A gas has four properties that are used to describe it. There is volume, temperature, and we've seen temperature and volume before. And then actually moles is given actually a one-letter character, and it's lowercase n. And I don't know why they chose n, probably because m is already taken for other things. And then there's actually a fourth, so we've seen volume, temperature, moles, but there's actually a fourth property, pressure. Because gases can be compressed, they have this property of pressure. And so depending upon how compressed they are, they'll have different amounts of pressure. And so since the fourth property is new, we need to define the new property. Pressure is equal to force divided by area. So if I have a container, I could imagine a tire or what have you. So the particles in here are moving around. They bounce off of each other, but they also bounce off of the container walls. Bouncing off the walls creates that property of pressure. One of the most common units, does anybody know the unit? What's the pressure unit when you fill up your tires?
PSI.
Yeah,
Pounds per
PSI.
square inch. Pound square inch.
Yeah, pounds per inch squared, or pounds per square inch. So pounds is actually mass accelerated by gravity, is a force, and inches squared is an area. So actually the English unit of pressure kind of relates really directly in a very direct sense to our sense of pressure. I guess my question is, if my tires are flat, what is the pressure? Is it really zero? When the tires are flat, the gauge pressure is actually the pressure above the atmospheric pressure. Here's the world, and here's me on top of the world, okay? And, or somewhere in the world, I guess it doesn't matter. If it's a circle, I could be at any point, right? But at any rate, there's atmosphere above me. So if I cut out a square meter of atmosphere, there's this giant atmosphere, and those are particles, right? And they go up actually a couple miles into the sky. They're more dense down at the bottom, perhaps, and maybe a little less dense up here. But at any rate, there's a whole ton of particles above me. And those particles have mass, and they're being accelerated times gravity, which is a force, right? There's a downward force on me. So let's label it. This is the atmosphere, right? So everybody's under pressure. Perhaps we don't think about it because it may be in the same way that a fish doesn't think about the fact that it's in water. It's just its natural state, right? Okay, now I'm going to ruin the drawing. I'm going to make it even worse. And it's exaggerated for effect, okay? So now, let's say this is Mount Everest, okay? And this is obviously out of scale, right? But here I am on top of Mount Everest. What happens to the pressure?
It becomes higher?
Well, how much?
It decreases. There's less particles hitting you, so you have less pressure, right?
Yes, yeah. So that's exactly right. The amount of atmosphere above me is much less. It's only this much. So lower pressure. So actually at sea level, in the unit we talked about, it's 14.7 psi. And that's actually, as a scientist, that's not the unit that we are going to use. Galileo and some of his contemporaries would measure pressure. They'd get a long tube, and then they'd fill it with mercury. And then they would take this tube and they would flip it on its end. So the tube is now like this, yeah? And then into a dish. And the mercury would drop, actually. So it wouldn't stay at the top, but it would drop a bit. Some people say the vacuum is keeping it from dropping. That it's not actually the vacuum, but it's actually the outside pressure. If there was a hole in the tube up here, let's say it's up here. If there was a hole in the tube up here, then the pressure would be pushing down on the column, but it's not, right? The liquid inside the tube does not feel the pressure. But outside, there's atmospheric pressure that keeps the mercury from spilling out of the jar, right? There's the mercury's here, and it comes out, but then it doesn't just spill all the way out. You don't empty the tube, right? But it fills up this little tray. And so this is another way of measuring the pressure. They measure the pressure from the liquid in the tray to the top here, the height of the column. And they measure it in millimeters of mercury. And so at sea level, it's about 760 millimeters at sea level. This is on average, right? Pressure in PSI is also 760 millimeters of mercury. And this is an average pressure. I can have hot days where it's the particles are moving faster and they will have higher pressures, not a lot higher. And I can have cold days, when the particles are moving slower. But this is like I guess imagine average temperature, this would be the pressure that exists for that average. And so this is another way of measuring the pressure. And this actually corresponds to your iPhone. If you guys want to, you could go to your iPhone and click on your weather app or your smartphone. This is also 29.94 inches of mercury. This is also equal to 14.7 psi, pounds per square inch. But this level of mercury above its, when I take a tube of mercury and invert it, that height is a nice way of measuring pressure. This is kind of English units for barometric pressure. I don't know if anyone's ever gone sailing, but when you look at the barometer, it measures this pressure. And when the barometer pressure changes, usually that means the weather is going to change. So if the barometer pressure increases or decreases, then it might be getting windy and a storm might be moving in. So it's very useful if you're on a boat, right, to know that pressure. But if you look at your weather app and you scroll all the way down, you should be able to see, while I'm on this topic, there's many other units of pressure. So I'm going to mention a few others. So for a while, let's just say that 760 millimeters was the SI unit of pressure. And you guys know what they did, right? And then what they did is they created a new SI unit. They said, let's have the average pressure on the planet be 1. And we're going to call it atmosphere for atmospheric pressure. So this is also, all these units are equivalent. And ATM, and that's actually, this is the one, ATM is the one I'm going to teach. That one, it's still used very widely because it's really easy to relate it to. If you hear, oh, it's 32 atmospheres, then you have a kind of a reference point. You can say, oh my gosh, that's 32 times the pressure, that we experience at sea level, right? Or if you have half an atmosphere. But actually, that's not the newest SI unit. They went back to Geneva and they drank wine again. And the newest unit is Pascal. And so that is 101,325 Pascal. And that's actually become the new SI unit. 1 atmosphere is equal to 101,325 Pascal, which is equal to 101.325 kilopascal, which is equal to 1.01325 bar, which is equal to 760 millimeters of mercury. By the way, 760 millimeters of mercury has also been named after a scientist. So that unit can also be called torr. They usually do lowercase, or torricelli. It's a really good question. 1 Pascal is actually equal to 1 Newton per meter squared, right? And a Newton is equal to mass times gravity in SI units, which is the, it's a kilogram times 9.8 meters per second squared. Ooh, I'm sorry, it's not meters squared. It's, I screwed this one up. Now that I figured it, okay, so kilogram meters per second squared. Mass times acceleration is newtons, and then I divide that. So then Pascal would be equal to Newton per meter squared. I'm spending too much time on units, but at any rate, that would be kilograms meters per second squared per meter squared, which would actually give you, gosh, that would be kilograms per second squared times meters would actually technically be it. Those are units of pressure. And so, well, if we go back to this, so all of these are equivalent, and you'd be given, this is one long conversion factor that you can, and I'll give any of these to you that I want to use on the test. You get that whole thing, and you can cherry pick anything you want from it. Okay, so let's take this here, and then let's do a conversion. Convert 839 torr to atmospheres and PSI, just to show that we can cherry pick. And all of the other units are the atmospheres, the Pascal, the kilopascal, the bar, millimeters of mercury, torr, and even inches of mercury. Those are all exact because those are from the metric system or exact conversions from the metric system. But the PSI is a 3 sig fig approximation between them, right? So if I convert from any one of those other units to PSI, then I have a sig fig issue. Let's do the first one. So 839 torr, and I'm going to pick my equality. So my equality over here is 760 torr, right? This one is equal to 1 atmosphere, right? So I'm going to use those two. So I'm going to plug in my conversion. I want torr to cancel, so I'm going to put it on the bottom. 760 torr, 1 atmosphere. And so the torr cancel. And then I have that. And this one's 3 sig figs here. So my answer should be 3. My measurement had 3. And so that gives me 1.10 atmospheres. Let's convert it to PSI. So 839 torr. And my conversion factor now is 760 torr is equivalent to 14.7 PSI, right? And now this is 3 sig figs, but also the PSI is 3 sig figs. My answer still needs to be 3 sig figs. So I'm going to take 839 divided by 760, then times 14.7, and I get that's equal to 16.2 PSI. So that's converting between pressure units. And so using the same strategies, you should be able to convert any of those pressure units between each other.